In the previous video, we looked at the concept of angular momentum. In today's video, essentially what we're just going to do is work through sort of a simple problem on conservation of angular momentum. And the problem is this. It's from an exam I gave a few years ago in this class. It's basically you have a 225 kilogram merry-go-round with a radius of 1.5 meters spinning at 45 revolutions per minute on frictionless bearings. And then two children, each weighing 31 kilograms, jump onto it right at the edge of that merry-go-round and hold on. And the question essentially boils down to, well, how fast are they moving after they jump onto it? But I've split it up into two parts. Part A, what is the angular momentum of the merry-go-round prior to the children jumping on? And then how fast are they spinning afterwards? So this all boils down to conservation of angular momentum. If we look at our system as the children and the merry-go-round, there are no external torques about the axis of rotation, so the angular momentum about that axis is conserved. Or for our system, essentially the angular momentum of our system initially is equal to the angular momentum of our system at the end, before and after they jump on that merry-go-round. And just like when we were dealing with linear conservation of linear momentum problems, we can just break this up into the angular momentums of our system parts, right? We have the angular momentum of the merry-go-round at the start, plus the angular momentum of child 1 at the start, plus the angular momentum of child 2 at the start, is going to be equal to the angular momentum of the merry-go-round at the end, plus the angular momentum of child 1 at the end and child 2 at the end. And this is just conservation of angular momentum. So the thing we're going to need to do here is figure out, well, what are these angular momentum? Initially, those children are just standing still, presumably off to the side of that merry-go-round, so their angular momentums are both 0 at the start, right? And the total angular momentum of our system is determined by that initial angular momentum of the merry-go-round. So how do we calculate that? Well, the angular momentum of the merry-go-round is just going to be the moment of inertia of that merry-go-round times its angular velocity at the start. We'll just call that omega I, this initial angular velocity, right? The angular momentum the moment of inertia of that merry-go-round, well, we can essentially treat it as a solid uniform disk. That's a simple way to model it, in which case, looking up our table of moment of inertias, we know that the moment of inertia for that solid disk is 1/2 the mass times its radius squared. Or in this case, if we plug in the 225 kilogram mass and the radius of 1.5 meters, this gives us 253.1 kilogram meters squared for its moment of inertia. And if we have the initial angular velocity is 45 revolutions per minute, well, we could leave this in revolutions per minute, but we probably want to convert this into our standard radians per second. So how do we do that? We would multiply that by, well, 1 minute divided by 60 seconds. That's essentially multiplying by 1, and then the minutes would cancel, and we'd have it in revolutions per second. And then knowing that 2 pi radians divided by 1 revolution is equal to 1. There's 2 pi radians in 1 revolution. That would cancel the revolutions. That gives us what our angular velocity is prior to those children jumping on. And it equals 4.71 radians per second. So we know that the angular momentum of that merry-go-round initially is equal to 253.1 kilogram meters squared times 4.71 radians per second. This ends up equaling 1,192.8 kilogram meters squared radians per second, right? So that's our initial angular momentum of our system, because again, the children have no initial angular momentum. So we know that that's 192.8 kilogram meters squared per second. Now that's the answer to A. We know the initial angular momentum of the merry-go-round at the start. The question is, how does that relate to the end? Well, we know it's all going to be equal. So we know it's the merry-go-round's moment of inertia times its final angular momentum plus child one's moment of inertia times its angular velocity plus child two's moment of inertia times its angular velocity. And since they're all spinning together, they have the same final angular velocity. So this ends up just being the total moment of inertia of the child one, child two, and the merry-go-round times that final angular velocity. So if we wanted to solve for that final angular velocity, it would essentially be the initial angular momentum divided by the total final angular or moment of inertia, and that would give us our answer. And so it boils down to now just calculating this. We already know our total initial angular momentum. We can calculate that final total moment of inertia. We already know the moment of inertia of the merry-go-round. For the child, it's going to be the same for each of them. So the moment of inertia of child one is the same as the moment of inertia of child two. They have the same mass and they're at the same sort of radius that they're spinning around. And it turns out we calculate the moment of inertia of those children. We can treat them like point particles spinning around as the mass of the child, we'll use the lowercase m, times the radius that they're spinning about squared. So this I1 plus I2 ends up being just mr squared plus mr squared. So this ends up being 1092.8 kilogram meters squared radians per second, all divided by 253.1 kilogram meters squared plus 2 times mr squared. That ends up being 139.5 kilogram meters squared. If we plug all of that in, the final angular velocity is 3.03 radians per second. And we figured out how fast they're spinning at the end. Hopefully you followed that. This is making sense. Again, it just boils down to there's no external torques acting on the system. That angular momentum is going to be conserved. Add up the total angular momentum at the start, set it equal to the total angular momentum at the end. Because it's conserved, they have to be the same. After that, it's pretty much algebra to solve for what was asked. If you have any questions on this, we're going to go over it more in our synchronous sessions. And you can always email me as well, and I'll get back to you.